I'm Scott Yilek. This is joint work with Tom Ristenpart, University of Wisconsin. So the motivation for this work is format preserving encryption. And so we have an example here where we have a database. On the left, we have some names, and then we have some social security numbers. So in the US, we have these 9-digit identification numbers. And we would like to keep these things secret in the database. We'd like to encrypt them. And so the question is, what do we use? And ideally, we want in-place encryption. We don't want to just throw AES at it and get something that's too big for this database column we already have. So ideally, we'd like to start with our 9 decimal digits, encrypt it, and still get 9 decimal digits. We want to preserve the format. Okay, and this is actually an important problem in practice. An entire industry is formed around the solutions to this problem. Okay, now in building these things, the key cryptographic challenge for us is actually then going to be constructing small domain block ciphers. So for our example here with 9 decimal digits, it'd be great if we had a block cipher that worked on 30 bits. Okay, now that's not all that straightforward. We have AES, but that's 128 bits. That's way too big. So we're going to need some other techniques to get these smaller domain block ciphers. So here's what we want for security. We want our small domain block cipher to be indistinguishable from a random permutation on that same number of bits, even if we give the adversary, say, Q input-output pairs for the permutation. And in this talk, I'm actually going to focus instead on what we're calling full security. And so with full security, we want our block cipher to look like a random permutation, even if the adversary is able to learn all of the input-output pairs. So you give them all 2 to the n input-output pairs for the block cipher, and it still should look like a random permutation. So why are we targeting full security? Well, the name, small domain, already tells us the domain in this case isn't very big. And a big N here, 2 to the n, is not very big. For example, for our example with n is 30, big N, the size of the domain, is only about 1 billion. The other thing we want, well, parameter selection ideally shouldn't depend on this number Q. If you're building a system and you're trying to decide how many rounds to use in some block cipher, it's very difficult to predict how many queries you're worried about. And so ideally, we'd get full security, and then we can just base our rounds on this size of the domain n. So there are some approaches you may have heard about in the last few years, a couple of these at Crypto. And these are not fully secure, like I said, we're targeting. So I'll call them partially secure approaches. So Black-Rogaway in 2002 had a Feistel-based scheme for this problem. More recently, 2009 here at Crypto, Morris, Rogaway, and Steggers analyzed the Thorpe shuffle, which is equivalent to a maximally unbalanced Feistel network. And they were able to improve the bound. And then just last year here at Crypto, Hung, Morris, and Rogaway introduced the swap-or-not cipher. And so again, they are improving the bound with each iteration of these papers here. But you'll see they're still not quite at full security. Ideally, we'd like to go into this swap or not bound here and get rid of the minus epsilon. We really want full security out of this. So there are some approaches for this. So there's the Knuth shuffle. Granbolin and Porning. FSE 2007 had another one. Stefanov-Shi actually had a follow-up to that just last year. They call fast PRP. And Morris actually gave a more detailed analysis of the Thorpe shuffle. And it's, some of these are OK, but they have some drawbacks in different situations. For example, you see a couple of them here have a big setup time where you actually have to go through the entire domain. Okay, so those are maybe more appropriate for much smaller domain settings. Granbolin and Pornin, they have a really clever shuffling routine. We'll talk about that. Our work's actually based on what they did. The big bottleneck there seems to be they have all these floating point operations needed to sample from the hypergeometric probability distribution. And Morris as well has logged third n rounds. So our approach, which we're calling mix and cut, I'll throw into the table here. We're actually going to have log squared n rounds. And we'll talk more about efficiency and some concrete numbers, AES calls, later on in the talk. But I think I'll just jump right in and describe mix and cut for you. So like a lot of work in this area, it's easiest to describe our cipher as a card shuffle. So you want to think about every point in the domain as actually being a card in a deck. And what we're going for is a uniform shuffling of that deck of cards. So let's take a look at mix and cut on an example with 8 cards here. So as the name suggests, what we do first is we lightly mix this deck. Okay, we're actually going to use swap or not, that cipher from last year's Crypto, to do this. And you want to think about this as kind of lightly shuffling the deck. It's certainly not enough shuffling to already get a full shuffle, but you're just kind of lightly mixing it. At this point, you're going to cut the deck. So you're going to take the top half, throw it over to the left, take the bottom half, put it over there on the right, and then you're going to recursively shuffle each of these two halves independently from each other. So this will look like this. We'll do mix and cut on each of those halves. We'll end up with 4 piles of 2 cards each. Then we repeat it again on each of those piles, and we end up finally with 8 piles, 1 card each, and we're done at this point. We just have to gather those cards back together into our fully shuffled deck. Okay, so this is just a simple example of mix and cut on 8 cards. And it's actually pretty simple to just give pseudocode for this. And then, so I put this up here because I want to emphasize this part with the repeat R times. That's the mix phase. So if you're not familiar with swap or not from last year's crypto, those basically 4 lines inside of that loop, that's swap or not. So the way that works is that you have a point X, and then you have a random key K, and X, I like to call it, it gets a buddy point, K XOR X. So you have two buddies here, and you flip a coin and you decide whether to swap those things or to leave them in their original positions. And so you just repeat this process over and over again for some number of rounds. So that's our mix phase, and then as I already described, then you just cut the deck, recursively call mix and cut, and gather everything back together at the end. So you might be wondering, how did we come up with this? Where did this come from? What were we inspired by? Well, our big inspiration was that GP cipher I mentioned earlier from FSC 2007. So let me describe that in a little bit of detail. So again, I'm going to focus on shuffling 8 cards. And I've actually numbered the cards here, ace through 8, because I want to emphasize one particular thing about the GP cipher. And so what they do is they use sampling from the hypergeometric probability distribution to randomly assign cards to one of 2 piles. Okay, so there's n, choose n over 2 ways to do this. They want to randomly choose one of those ways. Okay, so we've done that, and then we, kind of like we just described with mix and cut, we'd then go and we'd recursively shuffle each pile in the same way. Now something I want to emphasize about their shuffle is you'll see that the relative ordering of the cards actually stays the same. So if you look at the left pile, they're increasing as you go left to right, ace 2, 4, 7, same with the right pile, increasing as you go left to right, 3, 5, 6, 8. Okay, so the important thing here is to randomly assign to piles. It's not so important the ordering within the pile. Okay, the recursive call, in a sense, will take care of that later. Okay, so this is great. It's very clever the way they did this. Unfortunately, the performance bottleneck seems to be this need to keep doing hypergeometric probability sampling. Okay, so that involves quite a few floating point operations. We'd like to instead replace that with something more efficient. So that was really the big motivation. That's the big question we're trying to answer. Can we replace this with something much more efficient? So our answer is going to be yes. And in doing so, we actually developed a new framework for constructing fully secure PRPs from a new primitive we're defining that we're calling pseudorandom separators, or PRSs. Okay, so it's worth looking visually at our framework here. So first, we're gonna show you how to go from a PRS to a PRP. Okay, so I'll tell you on the next slide what a PRS is, and then we're going to go to a PRP. And we'll do this with what we're calling the Icicle construction. Okay? And then, of course, the question is, how do we construct this new primitive, this PRS? So I'll show you, we can actually get that from a PRF. There's a very simple lemma involved, and that's actually where we're gonna then insert this swap or not cipher from last year. Okay, so this kind of serves as an outline for the rest of the talk here. So let's talk about what a PRS is. What is a pseudorandom separator? Well, if you think about shuffling again, shuffling cards, a gamma pseudorandom separator is going to randomly assign the cards into gamma piles. And it's not so concerned with the ordering of those cards within the piles. So I think the best way to think about this cryptographically is that a gamma PRS is a permutation. So we want a permutation Z here. And we're going to look at the first little gamma bits of output. And we want those to be indistinguishable from the first little gamma bits of output from a random permutation. So those are the blue ones there. I want those to be indistinguishable. And I've actually blacked out the other bits to emphasize that I'm not concerned on those, at least from security perspective at this point. Okay, and we'll actually, one additional thing is we'll need separators that support tweaks in the sense of tweakable block ciphers from Liskov, Revest, and Wagner. All right, so here's the Icicle construction. We have PRSs now. We're going to focus on 2 PRSs, so like GP, randomly divide things into 2 piles. So how do you take one of those and get actually a PRP out of that? So we're going to start here with 4 bits. Each box represents a bit. And in the first stage, we're going to send these into our first separator, Z1. And interestingly, we're trying to build a permutation on n bits. And the first thing we do is actually apply a different permutation on n bits. But of course, these things have different security properties. Okay. So at this point, the leftmost bit drips down actually all the way to the final output. And at this point, we're done with that in the output. Okay. This is the end of the first stage. Now we take the other 3 bits, and we send them into the next separator, which is a permutation on 3 bits in this example. And importantly, the output bits that we've figured out so far that have already dripped down to the output, those have to be used as a tweak, as an extra input into this Z2. Okay, and intuitively, the reason we need this is, if you think back to our shuffle, we're dividing into 2 piles and then recursively shuffling those 2 piles. We want those recursive shuffles to be independent of each other. Okay, so the tweak helps us ensure that that's the case. Okay, now again, the leftmost bit drips down to the output. We continue on in this same fashion, using the output bits as tweaks, using the other bits as input into these permutations, until finally we just have 1 bit left at the end. That becomes part of the output. And all these bits that have dripped down now make up this output. And Tom thought this looked like an icicle, so that's why we called this the icicle construction here. It resembles a roof with some icicles coming down. Now, the key security theorem here is that if these Z's are fully secure pseudorandom separators, then this entire icicle construction actually gives us a fully secure PRP. Okay, so kind of bouncing back to our outline here of our framework, that's the right part of this. So we've gone from PRS to PRP with this icicle construction. But that, of course, still leaves the left-hand side here. How do you build a PRS? We need a fully secure pseudorandom separator. How can we get one of those? Okay, well, we already told you one of them, really. The GP paper had that hypergeometric sampling routine. That actually automatically gives you a fully secure 2PRS. But again, the problem with that was there was that performance bottleneck with all those floating point operations. So now our question that we're trying to answer is a little bit more precise. We're trying to build a fully secure 2PRS that's more efficient than the one from the GP paper. So this simple lemma is going to get us there. It turns out that if we have a block cipher that's a secure PRP against n/2 queries, so this is what we would call a partially secure PRP, then the inverse block cipher actually is a fully secure pseudorandom separator. Okay, so if we have a block cipher secure against n/2 queries, the inverse is actually a secure PRS against all n queries. You can just sketch the proof briefly here. So the reduction has to simulate all n 2PRS queries here, but it can only use n/2 evaluations of the block cipher E. And those evaluations are going right to left in this picture here. And so what you do is you'd pick all the blue points down there at the bottom, all the points starting with a 1. You send them right to left through the block cipher, and you'd learn all the points on the left that are mapped to the bottom half right there. Okay, and if you know that, then you also know that the other points must be mapped to the top half. So now you know all n points, the first bit of the result if you send them left to right through the inverse block cipher. Okay, so if you have that information, you have enough to answer these PRS queries. Okay, so this lemma now gives us a fully secure PRS as long as we have a PRP that's secure against n/2 queries. Well, as I mentioned earlier, the swap or not cipher actually, it meets that goal. It's secure against n/2 queries. And so we can plug that in as the 2PRS into the icicle construction, and the result is actually going to be a fully secure PRP. Okay, so let's talk about some efficiency numbers here. Okay, so let's go back to our example with Social Security numbers. That domain was size 2 to the 30. And so if we want a full security advantage of less than 2 to the -10, it's going to need about 10,000 rounds of swap or not. And the way we implement swap or not in this paper to support the tweaks, that's going to result in about twice that many AES calls, so about 20,000 AES calls. So while this isn't as efficient as partially secure ciphers like swap or not or the Thorpe shuffle, keep in mind it is getting full security, and it does have some distinct advantages compared to those other fully secure schemes that I mentioned earlier. Our main goal here, of course, was avoiding those expensive floating point operations of GP. Instead, now we're just doing AES calls. We don't have any of that costly setup time from the Knuth shuffle or the Stefanov-Shi result, and so we've avoided that. So our results should work well as we get domains that are going up n equals 30, 31, 32, whereas it starts to become intractable to go through the entire domain in those cases. And similarly, it, at least to me, is not clear how to tweak those two shuffles with that setup time. So if you want a cipher that supports tweaks, it looks to me like you'd actually have to go through that entire setup for each different tweak that you want, whereas our construction is actually very easily tweaked. Okay, so I'll just mention an extension here. I've focused solely on bit strings so far in my description here, but for a lot of applications, social security numbers being one of them, it might be more useful actually if we had ciphers that worked on a more general domain, say 0 through big N minus 1. Okay, so how do you make our results work for this? Well, you actually have two options here. The first option is probably the simpler one. Everything I talked about actually easily generalizes to other bases. So we focused on base 2 here, but you can imagine with social security numbers, credit card numbers, it might be best to use base 10. And so think back to that Icicle construction. We were dripping down bits into the output. You can instead think of that as dripping down an entire decimal digit into the output and then sending the remaining decimal digits into the separator for the rest of the construction. Okay, so that's kind of how it would work. As a shuffle, it would correspond basically to putting things into 10 piles and recursing. Option 2, maybe you have a specific domain you're interested in. It doesn't seem like any different base will work well for you. You could also actually just cut the deck into 2 uneven size piles. And this is actually what GP did in their paper. You could have one pile with size floor of n over 2, the other with ceiling n over 2, and then you'd recurse on those, and things still work out. Okay, and either option you choose here, the one little caveat, the one thing you need to do is you need to use the generalized version of swap or not. As I described swap or not earlier, we were using bitwise XOR. Instead, we'd have to use the generalized one, also from last year's crypto paper, and the same bounds apply to that. So no big deal there. Okay, so just mention some future directions here. So I think the most obvious future question to ask here is whether there are better direct constructions of PRSs. So we actually took something that was already a partially secure PRP, swap or not, and used that to get our PRS, our pseudorandom separator. But it could be the case that there's a much, much more efficient construction directly of say, a 2 PRS. And intuitively, it seems kind of easy, or it should be easy. For a 2 PRS, we only need one of the bits to look random, to look like a bit from a random permutation, whereas the other n-1 bits, we don't really care about. So intuitively, that should be something we can construct more efficiently than a full block cipher. But it remains to be seen. And stepping back a little bit, I think we'd really like to close this efficiency gap between the in-use scheme. So there's a proposed standard for this with FFX. I believe they do balanced Feistel with only like 10 to 15 rounds. So that's very fast. We have swap or not. We just described that. That's partially secure, but it's actually still quite fast. And then we have our new cipher we've described on the spectrum here. That's mix and cut. It's fully secure, but yet requires more rounds. And so we'd really like to close this gap between what's been proposed in standards, FFX, and now our new fully secure scheme here, mix and cut. Okay. So with that, I'll just leave the summary of our contributions up on the screen here and take some questions.
Okay, thank you, Scott. So, are there any questions? Okay, so I have one.
Oh, yeah?
So are there any sort of inherent lower bounds on the relation between the setup time, the encryption time? So you lowered something from log cubed n to log squared n. Can you?
Yeah, so it seems like the goal there really is to get log n rounds. And it seems like that's a fairly difficult problem. So that's a pretty good open problem. Now, asymptotics in the small domain setting, it doesn't really mean as much. We're more interested in hard numbers. And I think some of those numbers were maybe a little bit deceptive. The asymptotic bound might look worse, but actually in practice, things work out to be faster. So you need to actually look at how many AES calls there are, I think, to get a true view of the efficiency.
Okay, thanks.